An important feature of the Budgie app that hasn't been built yet is periodicity. This video is part of a series where I'm building a Phoenix app from scratch. All the code is on GitHub with a link in the description. I'd like to subdivide a budget into time periods so I know when I'm on track with my goals. More than that, it's natural to think in terms of some amount of money per month than the full annual amount. The other thing that we get out of these time periods is the concept of rollovers. If one month's budget isn't fully spent, it should roll into the next month. This also lets somebody borrow from a future month if they want to make a bigger purchase. To support this concept, I'm going to extend the data model of the application. Recall that previously we store budgets and transactions linked by a budget ID. My first instinct was to make transactions children of periods, which themselves would be children of budgets. But if we ever wanted to take an existing budget and subdivide it into weeks instead of months or something custom, we would end up having to break that hierarchy and restitch it together. The alternative, which we're going to implement today, is to make the budget period a sibling of the transaction that gives us an opinionated window into a subset of the transactions. For now, we're going to assume that budget periods are monthly and that budgets will align with the beginning of a month and the end of some future month. To enforce that, we're going to need some validations as well. So let's get started by setting up the budget period schema. In my terminal, I'll run mix Phoenix gen schema. This is going to be in the tracking context, and it's going to be a model called budget period. It'll be stored in a table called budget periods, and it'll have start date, end date, and a budget ID that references budgets. This command created two files. One is the schema itself, and a database migration file that describes how to create the table and indexes and whatever the database is going to need to store this information. Just like transactions, we should set the budget ID foreign key to cascade deletes by changing onDelete to delete all. This means that whenever a budget is deleted, all of the periods will be deleted automatically by the database. Then we can add a constraint similar to what we did in the past to say that the end date has to be greater than the start date, and we've got a little comment in here for future us. Finally, to make sure that these don't conflict with each other, and to help with the lookup performance of the records, let's add an index called a unique index to budget periods on budget ID and start date. The order of the fields in a database index is important because they essentially create a list of all records sorted by these values. And since the prefix is budget ID, this index can be used by the database to find periods by budget ID. This means that we can delete the original index that is just by budget ID. Let me show you what I mean. In a database, records are stored in a certain order on disk. In this case, we've got things that are commingled between budget 123 and budget 456. A database index is a structure that sits next to that table that's stored on disk and is essentially an ordered listing of where to find data. So in this case, if we have an index on budget ID and start date, then we're going to have in order a reference to the first record of budget 123, the second record of budget 123, and the third record of budget 123 without needing to scan through the whole table to find the items we're looking for. All of the records for this first budget are going to be here in order by their start date, and then for the second budget and so on. Now, if we just needed to look up all of the periods under this budget, this index will meet our needs. But if we had an index that went the other way, one that started with the start date and then went budget ID, let's see what that would look like. Down here, this index will have all of our Januaries, then all of our Februaries, then all of our Marches, and so on, where whenever there's a conflict on start date, we then have a tiebreaker of the budget ID. This can be scanned in order to find everything in a time period, but if we only had this index and tried to find all of the periods that belong to budget 123, we'd probably have to scan through the entire set to make sure that we find all of the items. It's important to get the ordering of the fields inside of indexes correct to get the performance characteristics that you're looking for. So naturally, you might be thinking, why not just create a bunch of database indexes? And the problem there is every single one of these will slow down any write operation you're performing to the database. Think about it. If I added a new period here, I would need to find the place that that period goes in each of these indexes, update them, potentially reallocate memory. It's a really expensive thing to do. So use database indexes to your advantage to optimize your reads, but don't go too wild with it or you'll end up hurting all of your writes. So with that out of the way, we can run mix ecto.migrate and start implementing. Over in our schema module, we should update our change set to catch the things that we just added in the database. But first, let's make it so that this budget ID isn't just a binary ID field. Instead, it should be a reference to a budget object. Then, down in our change set, we can make sure that budget ID can be written. And let's add the check constraint and unique constraints so that if we run into these errors thrown by the database, we end up catching them properly in our change set. Over in the budget schema, let's make sure that the other side of the relationship is understood by adding has many periods to the budget. Over in our test factory, we can add budget periods so that they can be written correctly in our tests. This will just be helpful when we're filling out those tests. Now, since we're planning to scope periods to represent months for now, we should make sure that they always start on the beginning of a month and end at the end of that month. Let's write a test with this expectation. So down in Budgie, I'm going to add a test file under tracking budget period test. And this is going to be a data test that ensures that our change set is doing the right thing. We want to make sure that when the start date is after the beginning of the month, we get an error. When the end date is before the end of the month, we also get an error. And when the start and end date are both incorrect, we should get 2 error messages. And finally, the change set should be valid if we give it all of the attributes that we expect. If I run this test, all 3 of those cases fail. And that makes sense because we haven't actually implemented this logic yet in our change set. So, seeing it fail, we're ready to add that validation. I wrote it up as a function with a couple of heads. Let's walk through it. Recall that validators are just functions that take in an Ecto change set and return a change set, potentially accessing fields and adding errors if they object to the change. The first function clause ensures that we're only running this validation when the change set would otherwise be valid. We don't want to check the start date when it's an invalid date to begin with. If we have valid start and end dates, we can run some conditionals. The date module built into Elixir comes with some very helpful utilities, including beginning of month and end of month. Using them, it's very easy to validate these fields. If I add this to the end of our change set function and rerun our tests, everything comes back green. In the future, we can always come back and update the application code to respect concepts like weekly periods, since the data model will give us that flexibility, and this validation is just being done in application code. Thinking about it more, we need the same validation on our budgets so that they can be subdivided cleanly. Rather than having the validation exist inline within the budget period schema module, we can extract this function into a new module for all of our common validations. I'll do that by creating a new file, and we'll call it validations.ex. This will be a new module, and it will have just this function in it. Now, there's currently some errors because these functions don't exist yet in this scope. To fix that, I'm going to import every part of Ecto change set. That way we can use change set methods in our validations. And now this has succeeded. So if I go into budget period, instead of having this inline, I can replace this with budgie.validations.validate date month boundaries, and the test should still succeed. Now I can grab this and add it to budget.ex in the change set function. If I run the tests again, I expect a failure. This is because we never intended to have this validation in our tests to begin with. This is simple enough to fix. In order to make this test fail before, What I did was just swap around the start date and the end date to make them incorrect. But the thing is, this is now an invalid start date as well, because December 31st is not the beginning of a month. So I can just change this, and now it would be December 1st to January 31st. And if I run the tests again, I should be down to 1 failure. And I bet that I did the same thing in this test. Yep, there it is. I can just swap those out with something that would be otherwise a valid start date and a valid end date. And now everything is succeeding again. With these tests succeeding, let's think about how these period records should be created. One tricky part is to write a function that generates all of the months in a given date range. This can be expressed in a recursive function that I'm going to call months between. Let's add it to our budget module. Now, this function is pretty dense and might be a lot to take in for people who haven't written very much Elixir or functional programming in general. This is a recursive function, meaning that it calls itself down here with a different set of inputs than it was originally called with. Going back to computer science class, recursive functions start out with what's called a base case, the situation where we want to stop the recursive calls. And then if we don't hit this base case, we come up with a way of the next call so that everything will cooperate and in the end give us the result we're looking for. If we've gotten to the end of the time range, that is, if the end date is not after the current end of the month, then it's time to return the list of months. But what's this reverse about? Those of you who have watched my Elixir 1.18 release video might have an intuition around this. Lists in Elixir are actually what's called linked lists. This means that each element points to the next one. Let me show you what I'm talking about. In many programming languages, arrays are just blocks of uninterrupted memory with slots. If you want to add to an array, all that you have to do is insert an element in that certain slot. There's two major downsides to this approach. If the array gets bigger than what's allocated, the program has to ask the operating system for an even larger uninterrupted block of memory, and this game of Tetris takes time. The second downside is that copies of the array also get updated, since they're all pointing to the same variable. On the other hand, Elixir references are immutable. This means that if you have a list, nobody else can edit the list from under you. Any operations that edit a variable actually create a new copy of it. That may sound like a disadvantage at first, but it just means that we need to think more carefully about how we build our systems. So, like I said, a list in Elixir is a linked list. That means that each element might point to another element, which points to another element. They're linked together. They don't have to be a continued block of memory, they just need to be a chain. Naively, if we just appended to the list, we would have to walk through each item one by one, trying to find the end of the list. And once we find the end of the list, we have to edit this final element so that it points to the new item. So what we have to do is create a node that represents this fourth item, and it's not pointing to anything next. Then we have to create a modified copy of element 3 that points to this element 4. And then, because we can't edit number 2 to point to this new 3, we have to create a new 2 and a new 1. We have now created a new node and then a new copy of every single item in the list. This is the worst case scenario for linked lists. Now, they don't have to take up an uninterrupted block of memory, but it was a huge operation. But there is something we can do here that's really cheap. When we're building a list, let's just build it in reverse. We just add this new item to the front and link it in place. We get to retain all of the other items with no problem. At the end, we just have to do one reverse operation to get our result. While this may feel like a roundabout way of doing things, imagine that this list was being used by thousands of other processes in parallel. No other process could corrupt the memory of any other, and we only need one copy of that list to serve all of those processes. Immutability is one of the major strengths of many functional programming languages. But when it's misunderstood, it can lead people to thinking that a language is slow or bad. In reality, it's all about how you use it. So with that knowledge in mind, let's go back to our function. For each month that we calculate, we add to the beginning of a list the record for this next month. And then when we reach the end, we just take the list and reverse it. It's easy enough to add some tests to make sure that this is doing what we're expecting. Over in the tests directory, I'm going to create a new file. In this test, we're going to make sure that two properties are satisfied. One is, when we're given a range of just a single month, we end up getting back just that month as a single period. And then when we give a quarter, that is 3 months, we get back those 3 items in order. If I run the tests, everything succeeds. This function is able to recursively construct the list of periods necessary for a budget. Now for the interesting part. When we create a budget, let's make sure that we also insert all of those periods into the database. It turns out that Ecto's change set module has a function called cast association. This is similar to the regular cast function that operates on fields, but instead it operates on associated resources. Put simply, we can treat related resources as though they were fields and tell Ecto to insert or update them to match what we provide. If you're coming from Rails, this is very similar to the accept nested attributes for macro. So in budget.ex, we'll add a new function. This is called add periods. When the change set is invalid, it's not going to do anything. But when the change set has been validated up to this point, it's going to grab the start date and the end date, calculate the months between those dates, and store that under periods in the changes on the change set. Then we run this function cast association on the periods field. And what'll happen is behind the scenes, Ecto is going to take whatever is on the periods change and run it through the change set for that schema. Because it has knowledge of the associations, it will also insert the newly created budget ID into that change. So all that I need to do is run add periods at the end of the change set, and it should do exactly what we're looking for. So I'll open up the app and create a brand new budget. And let's start it in January and end it in March. If we create this budget and then grab the ID, we can take a look in the database and see what happened. So we'll select from budget periods where the budget ID is that ID of what we just created. And let's make this a little bigger. We can see that there are 3 periods created with a start date in January, February, and March, all associated with that same budget, all inserted around the same time. Those of you with backend experience might be wondering, what happens if this fails in the middle of inserting the data? Luckily, Ecto automatically uses database transactions when operating on associated data. If I look at the application logs, I can see that the budget creation was wrapped in begin and commit. Those 2 SQL keywords indicate a transaction. That is an operation that needs to succeed all at once or fail all at once. If the server crashes before the commit runs, the database will roll back the changes automatically. Database transactions are a deep topic that we don't have time to get into today. Just know that begin and commit are important, and they're used in Ecto when we're doing cast association. Now, let's go into the UI and load budget periods to prepare for the future. First, we'll go into the budget show live template file and add a new list. We'll add it right here. And of course, there's an error because periods was not loaded. Remember that Ecto doesn't lazy load by default. So if we go into budget show live, Where we currently load the budget, we only preload the creator. Let's change that and preload the creator and the time periods. Now in the UI, we can see those January, February, and March records. We've added a new model with custom validation and laid down the foundation for an important structure in the Budgie app, allowing it to change in the future, but keeping it rigid today. I'll fill in some more tests off camera in a linked pull request. Next time, we'll wire in the budget period concept with balances and rollovers in the UI, getting one step closer to that finished app. This has been Code and Stuff. Thanks for watching.